Given that the class bully weighs twice as much as me, I will have to move closer to the pivot point in order to balance out the weight. Since I am out of town, I could only find a standing seesaw. This is different than a normal seesaw because you have to lean backwards in order to balance out the weight. The measurements show that the two people standing normally on the seesaw are 49 inches apart. This also shows that both members are 24.5 inches apart from the pivot point, or 0.622 meters away. When leaning back, the lighter member is 0.8255 meters away. When standing normally, the lighter member has a torque of 401 and the heavier member has a torque of 553. When leaning back, the lighter member has a torque of 532 and the heavier member still has a torque of 553. When the torques are added together normally and leaning back, they are both around the 1000 mark. This shows that the lighter member has a higher torque when leaning back in order to balance out the weight. When swinging at the park, I believe the length of the swing has the greatest role in determining the period of your swing because the longer the length of the swing, the longer the period will be. Secondly, I think the starting position when swinging is the second most important because the higher the starting position, the shorter the swing time. When swinging at the angle, I calculated that our angle was 0.778 radians. The torque of the lightest member was 7107, the middle member was 8822, and the heaviest member was 9802. I determined this by using the length of the swing, which was 63 inches. After completing our swings, I determined that the length of the swing had the greatest effect on the period of the swing because it varied the times by around a second. It is relatively easy for the swingers to synchronize because mass has no bearing on the amount of time of the periods. For the normal swing, the lightest member took 2.14 seconds, the middle member took 2.84 seconds, and the heaviest member took 2.55 seconds per swing. For the angle, the lightest member took 2.65 seconds, the middle member took 2.9 seconds, and the heaviest member took 2.57 seconds per swing. For the shorter lever, the lightest member took 2.35 seconds, the middle member took 2.92 seconds, and the heaviest member took 2.75 seconds per swing. This clip shows the lightest and heaviest member of the group synchronizing their swings. This is possible because only angle and length of lever arm affect the period of a swing. I believe if my feet slipped, I would fall towards the center of the merry-go-round because I was facing the center of the merry-go-round. From the perspective of the spinning merry-go-round, the ball is being acted on by angular velocity and gravity. From the perspective of the observer, the forces on the ball are angular acceleration and gravity. When the ball hits the ground, angular momentum is acting on it. From the perspective of the rider, the ball fell straight down and rolled to the left. From the perspective of the observer, the ball fell at an angle and rolled left. The period for the outer points of the merry-go-round was 5 seconds, and the period for halfway points of the merry-go-round was 4 seconds. The period of revolution when the person walked toward the center decreased. The speed decreased because the period of time taken to complete one revolution decreased. In order for the angular momentum to be conserved, the person's speed must stay the same. I did observe this. I would like to add that the photography skills are pretty bad because my mom had to film this. Also, the little kids would not move off the merry-go-round, so I had to complete the experiment with them on it. Thanks!